Boa noite a todos que nos assistem. Hoje a gente vai ter a apresentação de um professor da Universidade da Flórida, o professor Agresti. Só que antes de falar um pouquinho do currículo dele, eu acho importante a gente comentar que nosso programa de Estatística Aplicada e Biometria, aqui da Universidade Federal de Viçosa, está com edital aberto. E vocês vão poder encontrar no link, né, no chat aí da apresentação, que o nosso edital está aberto e ele vai estar recebendo inscrições até agora em junho. Então, fique à vontade para entrar no edital, conhecer um pouco do nosso programa e se inscrever no nosso programa de mestrado e doutorado. Bem, sobre o nosso palestrante de hoje, o professor Agresti é um distinto professor emérito da Universidade da Flórida, amplamente reconhecido por suas contribuições significativas à estatística, especialmente no campo da análise de dados categóricos. Tendo ocupado cargos de professor visitante em universidades como, por exemplo, Harvard, de 2008 a 2014. Ele obteve seu PhD em estatística pela Universidade de Wisconsin-Madison, em 1972. O professor Agresti é autor de diversos livros influentes nessa área, incluindo Categorical Data Analysis, de 1990, An Introduction to Categorical Data Analysis, 1996, e o livro Statistics, The Art and Science of Learning from Data, 2006, dentre outros livros. Seus trabalhos têm sido amplamente citados e utilizados por pesquisadores e profissionais em todo o mundo. Além de sua produção acadêmica, o professor Agresti tem sido um educador dedicado, formando e orientando inúmeras gerações de estatísticos. Ele recebeu vários prêmios e honrarias por suas contribuições à ciência estatística e à educação, como, por exemplo, o Prêmio Estatístico do Ano, seção de Chicago da American Statistical Association, em 2003, dentre outros. Então, por favor, recebam o professor Agresti para a sua lecture de hoje.
Thank you, Luis.
Good night. Yeah, Professor Agresti, I just talked about your curriculum to the audience. So we welcome you very much. We thank you for your time to stay here with us and to lecture for a moment, okay? So feel free to start anytime you wish.
All right, thank you for the introduction, Luis. I appreciate that. And thanks to all of you for coming today to hear my seminar. I'm a bit sad not to be there in Brazil. I have nice memories of 3 times I was able to visit Brazil. Once, gosh, almost about 30 years ago, I guess, when Clarice Demetrio in Piracicaba invited me to teach a short course. And I was back there, I guess, about 10 years ago. And I'm once in Porto Alegre for a conference. So it was always a wonderful experience with such friendly people and such a beautiful country to visit. So anyway, I have fond memories when I think of Brazil. So my lecture today, it says simple ways to interpret effects in modeling binary and ordinal data. And what this primarily will focus on, we'll see that there's something called the odds ratio. That is a standard measure for interpreting effects in models for categorical data, such as logistic regression and log linear models. Some of you may not be too familiar with those, so I'll talk a bit about that early in my seminar. But the issue is, I don't think the general public really knows what an odds ratio is. So I'll show you ways you can try to fit models like that, but use alternatives if you have, say, a binary outcome, a success-fail type outcome, or let's say ordered categories like excellent, good, fair, poor, and you want to instead focus on probabilities that may be more understandable to people than a measure such as the odds ratio. My own interest in this is the following. You saw that I'm called emeritus professor. That's just a fancy way for saying that I retired some years ago. But I have, in my retirement, been working on various book projects, but not categorical data, but other things. A typical book, I might have one chapter on categorical data. So it's a challenge to explain complex models in just maybe 15 pages or so. So I've been looking for simpler ways of doing this in books and in teaching short courses. For instance, my most recent book called Foundations of Statistics for Data Scientists, published a year ago, is kind of a book in the theory of statistics, mathematical statistics, in which normally you prove lots of theorems, like the central limit theorem, the law of large numbers. But my co-author and I focused on using R and Python to do simulations to illustrate the ideas. And there we have a chapter on generalized linear models, a few pages on logistic regression, and we found it quite a challenge to explain these ideas so quickly. So my talk today, in which I'll talk about these alternative ways of coming up with measures for these models, is based on an article with a couple of statisticians in Italy. Claudia Tarantula, who's at the University of Pavia, a historic university near Milano. Roberto Variale, who's at La Sapienza University in Rome, which has one of probably the largest department of statistics in Italy. And we wrote a paper that was a recently published book edited by Maria Katteri and Irini Mustaki on trends and challenges in categorical data analysis. So first, just an overview of what is the odds ratio, how I think people interpret it as a ratio of proportions, how sometimes that's okay, but it can be very wrong. And we'll see the reason for considering this is that logistic regression, the most popular model for binary response variables, is most naturally interpreted with odds ratios. So a couple simple examples. First, a medical journal preventive medicine report on looking at things that affect the chance of getting lung cancer, point out that even if you're not a smoker, you still have some chance of getting it. It was estimated to be about 1.8% for males, 1.3% for females. So what's sometimes called the relative risk is the proportion ratio, the chance of a lung cancer conditional on being a male divided by the chance of getting lung cancer conditional on being a female. So 0.018 or 0.013, 1.38. The chance of lung cancer at 1.38 times as high for males as for females. What's the odds ratio? Well, the odds itself is a ratio of a probability to its complement. The probability of the outcome 1 divided by 1 minus that, the probability of the outcome 0. So a probability being between 0 and 1, the odds is any non-negative number, okay? The odds ratio, you do that for two groups and take the ratio. Find the odds for males, the odds for females, and take the ratio. In this case, for males, 0.018 divided by 1 minus that, females 0.013 over divided that. Now, both these proportions are very close to 0, so the complement proportions are very close to 1. So to get the odds, it's almost like dividing by 1. It doesn't really change it hardly at all. So the end result is something very similar to the ratio of proportions. So when the proportions are close to 0, you can interpret the odds ratio as just a ratio of proportions, and you're not off by very much. But move away from 0, and that is not true. Here's the result of a survey a few years ago in the United States asking, do you think dealing with climate change should be a top priority for the president and for Congress? In the survey, 78% of Democrats, people identified as Democrat, like President Biden is Democrat, for instance, said yes, they think it should be a top priority. Only 21% of Republicans, for instance, Donald Trump's Republican, only 21%. So the ratio of proportions, 3.7 times as many Democrats as Republicans thought it should be a high priority. When we find the odds ratio, though, it's nowhere near 3.7, it's 13.3. So, in fact, if you think of the odds ratio as being a ratio of proportions, you're way off. In a case like this, where the proportions aren't close to 0. And in fact, when the proportions get away from 0, it was shown in an interesting paper in the journal Biometrics a few years ago that the odds ratio is more similar to the square of the ratio proportions. In this case, the square 13.8, not so different from the odds ratio. So anyway, in my experience, I think most people can understand, okay, a ratio of proportions, but they're not typically used to interpreting ratios of odds. It's harder for them to interpret 13.3 than say 3.7 in this last case. Now, why is that relevant? Let's move on now to modeling binary data. The odds ratio turns out to be the key measure to describe how strong is the effect if we use a logistic regression model. So logistic regression is a regression model if you have a binary outcome, something like a success or failure. Does someone plan to vote for Biden or for Trump, for instance? And model that based on knowing their values of various predictors like their education, their income, their religious beliefs, their gender, their race. And then typically what you do in modeling is you take the odds ratio and apply some function to it, such as the log. That's called the link function, the function you apply to this probability. So logistic regression takes the odds and then applies the log to that, and that's what's called the logit. So that's why it's sometimes called a logit model instead of logistic regression. Now, why do this? Well, see, the right-hand side looks like what you have in ordinary regression. That could be any real number. The probabilities between 0 and 1, the odds, any non-negative number, the log of that could then be any real number. So that transforms the probability to the real line scale, which you use for linear predictors. Now, in this linear predictor, I should mention, I'm going to discuss cases where you really want to just compare two groups. So you have an indicator variable for something like females and males, and then you want to adjust for some other explanatory variables that you want to treat as covariates. So you've got maybe an x1, x2, up through an xp, p other variables in the model that you want to adjust for. So maybe you want to compare females and males while adjusting for income and education and race and various other things. So what is beta then? What is the coefficient of this indicator for the two groups you want to compare? Well, plug in z equal 1, find all this. Then plug in z equals 0 and find all this, keeping the x's constant. And the difference is going to be beta. Beta is the difference of the log odds between the two groups when you adjust for, keep constant the values of the other explanatory variables. So beta is a difference of a log of odds. Remember, a difference of logs is a log of a ratio, so that's the same as the log of the odds ratio. So once you fit a model like this to some data and you estimate beta, the typical thing you'll do is exponentiate your estimate and interpret that as an odds ratio. Now, historically, this sort of model started to become popular in the 1940s, 1950s. Wasn't really used all that much, though, until about 1970, after some software got developed. Before it, there was an alternative model called a probit model, which instead of this logit link uses an inverse of a standard normal CDF. I'll talk about this a bit more later to explain why this might be useful in some cases. And capital phi here is the standard normal CDF, which remember takes the real line and maps it to between 0 and 1, the probability value. So when we take the inverse, we're mapping the probability back to the real line scale. Okay, so what can we do if we find this a bit awkward? Because maybe we're working as a data scientist with some other scientists and they have no idea what an odds ratio is. We want to try to explain it more basically to them, how strong the effect is, what the difference is between these two groups. So let's see a couple alternative ways of doing that. A very simple thing you can do is don't take that logit transform, just model the probability itself. that's just the mean of the zeros and ones, the chance of success. Well, if this model is discussed in a book on categorical data analysis, probably it's kind of discarded quickly. The book will say something like, well, you can't do this very much because the probability's got to be between 0 and 1, and the right-hand side could be any real number. So you could end up getting estimated probabilities below 0 or above 1, which is not good. However, it turns out that if you're dealing with probabilities in the middle of the range between about 0.2 and 0.8, this simpler model gives essentially the same fit as logistic regression. And if we can use this model, what's the advantage? What's beta now? It's this probability when z equals 1 minus this probability when z equals 0. Beta is just a difference of probabilities, and most people have an idea of what that means. If you say the chance of something happening is 0.2 higher for females than males, they have a rough idea what that means, more so than an odds ratio. So let me try to convince you this, what I just said here, this is true. The next slide, I just randomly generated 500 observations uniformly from 0 to 100, and then generated ones and zeros to follow a logistic regression model where the probability of success would go from about 0.2 up to 0.8 as x goes from 0 to 100. So I jittered the data. You can see there's mostly successes at large values of x, mostly failures at small values of x. And what I'm showing here are the two fits, the logistic fit and the model just using the probability itself, what is often called the linear probability model. And you can see they give essentially the same fit. Okay, how about what if the probability is not between 0.2 and 0.8? Well, if it's small, if it's say below 0.25, it turns out you can just take the log transform. And if it's above 0.75, you could take the log applied to the other outcomes, failure instead of success. What's the advantage of that? Well, exponentiated both sides, that says the probability follows an exponential function. How to interpret beta? It's the log probability when z is 1 minus the log probability when z is 0, a difference of log probabilities. That's the same as a log of a ratio of probabilities. So if we exponentiate that, that's just a ratio of probabilities. Okay, so that's giving the sort of thing we were looking at in our first example here, just taking a ratio of probabilities rather than a ratio of odds, which is a bit easier to understand. So if we can use this approach for the model, it can be easier to interpret than the odds ratio in logistic regression. And here's an example showing that. I won't go through the details of how the data were generated, but the relatively few successes at big values of x, mostly failures at small values of x. And I'm not sure what you're saying. I have the slide numbers in front of what I'm seeing here. I don't know if that's true with what you're seeing on the screen there where you're following the seminar. I hope you maybe can see what's behind here, which I can't. But anyway, the point is these two curves are very, very similar. They give similar fits. Let's go to a real data example to try to make this more concrete. Here's an example showed to me by my friend Roberto Variale some years ago. It's based on a survey taken by the statistics group in Italy, what's called ISTAT, the Italian National Institute of Statistics. And it was a survey in Tuscany, Italy. Tuscany is the region near the middle of Italy where Florence is, for instance. And they measured the following things. Are you employed? Yes or no? What's your gender, female or male? Are you an Italian citizen? Yes or no? Are you receiving a pension? Yes or no? And then this was considered for two age groups, people over 65 and people under 65. So if we look at the elderly sample, over 65, almost 28,000 of them, here are the 8 possible scenarios, the 8 possible combinations of gender, female or male, whether Italian, yes or no, whether receiving a pension, yes or no. The sample proportions for those all 8 cases are all quite small. The sample size is quite large, and incidentally, these had to just be rounded for confidentiality reasons at VSTAT. So the proportions are small. We should be able to just use the log link as an alternative to the logit link. Okay, so here's what happens if we do that, and I'll show you in a little while how you can get such a fit. Look at the gender effect. For the logit link, the logistic regression model, it's a negative number, meaning when G is 1, the chance of it being employed is smaller than when G is 0. When you're female, less chance of being employed than when you're male. You still get a negative effect for the log transform, but you have a simpler interpretation. You can exponentiate that, and that says the estimated chance of being employed if you're a woman is only 0.29 times the estimated chance if you're a man. Okay, so that's the ratio of proportions. The odds ratio is somewhat different. These are giving very similar fits. I'll just mention it. If you found the estimated chance of being employed for all 27,000 cases for the 2 separate models, this link and this link, and averaged all the absolute differences, it's 0.0001. Okay. If you look at the younger sample, the proportions are near the middle of the range for all the 8 combinations of gender, whether Italian, and whether receiving a pension. So now we could instead use just model the probability itself. We could just model the probability itself. And again, we would see a negative effect of gender. What's the minus 0.139? It says the estimated chance of being employed, 0.139 lower for women than for men. Again, I think this is more understandable to most people than if you tell me odds ratio is, well, the odds that a female is employed 0.53 times the odds that a male is employed. Okay, again, the differences, the average absolute distance between the estimated probabilities for the 2 models is very, very small, so it's giving essentially the same fit. Okay, I'm going to just skip over the next few pages. If any of you want, you can take, I sent a copy of my seminar to the organizers, and you can, well, look at this on your own later if you want, but there's just a tangential effect. I think I'm going to skip over here. But I want to get to how we can use this information in practice now, because I have to tell you, I'm not saying stop using logistic regression. Logistic regression is by far the most popular model to use when you have a binary outcome, and that's going to be the case in the future. And there's good reasons for that. In practice, we typically prefer to use the logit link because it has greater scope. We don't have to worry about the probabilities being in the middle of the range or close to 0. It can apply more generally. But the point is, even if we use a logistic regression model, we can still use these types of summary measures that are easier for people to interpret. For instance, if we have n observations, and we've got an outcome for person I, and we've got, say, their gender, female or male, and they've got these other variables we're also measuring for person I, what we could do is go ahead and fit the logistic model, but then estimate what's the chance of success, say, if you're a female, what's the estimated chance of success if you're a male, and then average over the n observations all those differences, just to get something that's kind of like what you would get if you modeled the probability directly. It has something more like a difference of probabilities rather than an odds ratio. Or if you prefer to use ratios, you could, for all n observations, take the ratio of what you would get if you were female, what you would get if you were male at the various settings of your predictors for the estimated probability. Typically, you want to average them on a log scale, not the raw scale, which is very awkward for ratios of numbers. And then if you want to exponentiate that. So use logistic regression, but do these sorts of things. Now, it turns out the first thing I mentioned here has been around in an R function for some time. And again, I'm imagining most of you students have used R in courses you've taken. There's a package called MFX that can give you such a measure. It's referred to there as an average marginal effect. But what it means is you're just taking, as in our example, you're looking at what the chance of employment is estimated to be if you're male, if you're female, and then averaging all those differences for all the observations. So in other words, what you would do, you'd go ahead and use your software to fit a logistic regression model. With R, for instance, you can use the GLM function, generalized linear model, and say you want to model Y as a function of gender, whether you're Italian, whether you're in a pension, assuming you have binomial data and you want to use the logit link. That's going to give you logistic regression. Here I'm doing it for the younger sample. Then you can call up this library that I mentioned. It's been around for some time, and take your fit of your model and apply this function from that library that's going to give you, in this case, 3 numbers. For instance, the one for gender, this minus 0.14 is basically just giving you an estimate of what the average difference is and the chance of being employed if you're female compared to if you're male, about on the average about 0.14 lower for females than for males, adjusting for these other predictors. And you get a standard error for how accurate that estimate is, since after all, this is just a sample from some population. The label here seems kind of weird. This refers to the fact that if you had a quantitative predictor, you'd be looking at something like a derivative. You'd be looking at something like a rate of change of how fast that S-shaped curve is going up or going down per unit change in the predictor, and averaging all of those for all the people in your sample. So anyway, if you fit logistic regression and then do this, you're going to get numbers very much like what you would get if you actually use that alternative link function I mentioned instead of logistic regression. Okay. Next few pages, I'm going to just go over kind of quickly here too. I just mentioned that some of you may have heard of this idea of a generalized additive model. Instead of having the usual linear predictor, you use smooth functions for the predictors, and that allows kind of a wavy instead of a nice S-shaped curve. You can allow for different sorts of curve linearity. And I just want to mention that these sorts of measures could be useful in this case because you don't have any betas here to describe the typical effects, but you can get curves that you could still want to summarize by things like differences or rates of change. And for instance, some years ago in Florida, I looked at some data from a zoologist friend of mine who was looking at horseshoe crabs off the coast of Florida and the Gulf of Mexico, where there's the female crab surrounded by male crabs wanting to fertilize the eggs, and there'd be one regular male crab doing that, and then others who wanted to do it called satellites. And my zoologist friend was trying to estimate what affects whether a particular female crab has some of these satellites or not. And for instance, she looked at various predictors. What turned out to be important was how big the shell was of the female crab. It turned out the larger the crab, the more likely they were to have satellites. And then how dark the color was. As the female crab got older, the crab got darker. And it turned out that darkness had a negative effect. I won't go into trying to interpret the effect, but I just want to show you a picture. What you end up getting, instead of a simple S-shaped curve like in logistic regression, you get the following. Here, you got binary data, female crabs that have a satellite, female crabs that don't have a satellite, here plotted as a function of the width of their shell. Sorry, to go back and look at that. Is that, am I using, yeah, the width in centimeters of the shell. And as width goes up, the estimated chance is higher of having a satellite. And the two colors refer to the lighter color crabs, the younger ones, and the dark crab, the darker colored crabs. So if you're going to use the generalized additive model, it's also, I think, important to think about how can you summarize effects. So for instance, a non-statistician who has no idea what this model is can get a sense of what they're learning. And you can do things like look at average differences in these estimates. So these curves aren't parallel in any sense, but just as kind of a first-order approximation, you could take all the observations and just average the distance to up with kind of an average amount by which a lighter colored crab is more likely to have a satellite. And then for the effect of the width, you could do something like look at all the tangents to these curves, all the instantaneous slopes for all these observations, and get something like an average rate of change to show how quickly the probability of a satellite is going up as a function of unit changes of the quantitative predictor. So I just want to throw this in just to point out that I'm focusing on logistic regression type models. There's lots of other models these days that are used for categorical data where it's important to think about what are some simple ways we can use to describe effects. Okay, now to finish up my talk today, I'd like to show you how the logistic regression model extends to ordered categories and mention that there are alternative simple measures you can get there. By ordinal, I mean you have an outcome with multiple categories that have a natural ordering. So a subject who's given a drug for some disease is their recovery poor, fair, good, or excellent. If someone asks you about your political ideology, are you liberal, moderate, or conservative? So many categories, but a natural ordering of the categories. So such data are very common in the social sciences for questionnaires in which you're asked to show which of the set of ordered values you fall, also in medical applications for how well people respond to various treatments. So this has not received nearly as much attention in books as logistic regression, but there are lots of methods out there these days for handling ordinal data. And I think what's become most popular among statisticians in recent years is to take into account the ordering by focusing on cumulative probabilities. Look at the chance of being in category 1, then 1 plus 2, then 1 plus 2 plus 3, and model all those simultaneously in terms of your predictors. Let me show you a picture before I continue here. If you had, say, 4 categories, you use something like an S-shaped curve for all 3 cumulative probabilities: the chance of being in category 1, the chance of being in category 1 or 2, the chance of being in category 1 or 2 or 3. And because the cumulative probabilities are naturally ordered, you want these curves to be ordered. The curve for the chance of being in category 1 has got to fall below the curve for 1 and 2 combined, which has to fall below the curve for 1, 2, and 3 combined. Now, to keep this ordering, don't let these curves cross. In other words, you've got to have basically the same beta for all of them. They've got to all go up or go down at exactly the same rate. You got to have a certain parallelism, or one of these curves takes another one, just shifts it to the right or shifts it to the left. So what that means is, in your model, use the same betas for every one of the C-1 cumulative probabilities, the same betas. But you allow for the probabilities themselves to go up. As J increases, the cumulative probability goes up, so you have to have some intercept parameters that themselves go up. Okay, and then this link function, you can, well, in practice, most commonly, again, use the logit. In this case, the odds are the odds of being at the low end to the high end of the scale, and applying the log link to that. Or some other links. It's just historically the probe. This strange thing. I know this looks weird, but I got to try to give you some reason for why this actually can be a good thing to do in just a minute. The issue again is, how do you make sense of these betas, especially if you use a link function like this? If beta for a particular predictor is, say, 0.5, if you're looking at effective gender and the beta is 0.5, what does that mean? this thing changes by 0.5 when you go from being female to being male. Let me show you a couple things you can do. One is an underlying latent variable model, and then I'll go back to try to show you things on the probability scale. So I apologize, we've got a bit of notation on this slide, but it's a really important slide, so I'll try to explain it with a picture. In practice, when you have an ordinal response, it's often the case that you can imagine if you could measure it well enough, you could have a continuous variable underlying that you just can't really observe. A physician characterizes some response as excellent, good, fair, poor. People don't just progress in jumps, they maybe progress continuously. We just can't really measure that variable. So this is often the case. Another example, against political ideology, conservative to liberal, we can imagine a whole scale of potential values, not just 3 levels, moderate, conservative, liberal. So ideally, we might like to measure that continuous variable and use a standard regression model for that. Model the continuous variable in terms of something like a linear predictor plus an error term, where of course in normal regression, we're assuming that epsilon here has some normal distribution with variance that needs to be estimated. More generally, it has some cumulative distribution function that we could assume to be normal or something else. If we think it's going to be very skewed, for instance, and it's non-negative, we might use a gamma distribution. So suppose this is what we want to estimate, this beta. But we can't because we don't observe the underlying continuous variable. So let me go to the picture, then I'll come back to the derivation. So here's maybe what we observe, something like excellent, good, fair, poor, our observed scale. What we'd like to observe is this continuous scale where we have a nice curve, like a straight line, to describe on the average how y star behaves as the predictor x increases. So in the typical regression model, right, we've got something like a normal distribution around a mean at one value of x, go another value of x, we've got another normal distribution about the mean. The standard model assumes constant variability. And then you're estimating the beta, the slope of this line, to describe the effect. So what we'll assume now is, although we can't measure y star, although we're just going to measure y, 4 ordered categories, we'll imagine we're in the highest category if we're above some threshold here for the continuous variable, and we're in the lowest category if we're below some other threshold. And then pairs of these thresholds determine which category we're in. Okay, so for instance, the chance we're in category 4 at this level of x is just this area under the curve, and maybe we can estimate that when we observe our ordinal response. But what we'd like to estimate is beta, the slope of this line, even though we can't measure y star. So again, what I'm showing in this picture, the left axis is latent variable values, the right axis, what we observe, and the curves are showing the typical conditional distributions of the continuous response at different values of x. And this is the regression line that we'd like to be able to estimate. So let's go back now and use this construction. It says there's some thresholds, sometimes called cut points, between minus and plus infinity that determine where the observed response is, depending on where the underlying continuous response is. So if we're between the j minus first and jth of these, for the continuous variable, we're in category J, and that's what that picture showed. So what does that say about what our model should be for this cumulative probability? It's the same as the probability for y star being below the jth cut point, and let's just subtract off the mean, beta times x from both sides, and that leaves us with the error term. It's a cumulative probability for the error, but that's just what the CDF describes for the distribution of the errors. So that says that if we take G over to the other side, apply it as a length function to probabilities, take G over here to G inverse, we just have a regular type of what looks like a linear regression model, except a minus sign here instead of a plus sign. And in fact, some software uses that parameterization to have it coincide with what you'd like to observe for the underlying variable. Now, the nice thing here is, even if you just observe y and not y star, if you can fit this model for the cumulative probabilities for what we observe, you can estimate beta. Okay? So now, historically, the probit length was used with this construction if we want to assume an underlying normal distribution for the continuous variable. In other words, imagine that we would like to use an ordinary normal regression model, and we just can't because we can't observe y star. So that would suggest you have to use the probit length. And I'm sorry, I just skipped over a little bit of this. Maybe you can't see it with this thing in front of it, but anyway, that was shown a long time ago, but historically it wasn't used much after this was first shown. I think just because, partly because it was a little simpler to look at the logit link and get an idea of what it meant if you didn't appeal to the latent variable model. And then there's other reasons, for instance, in biostatistics and in applications with case control data, you can estimate an odds ratio and fit logistic type models with such data where you can't use other link functions. So logistic regression became more popular. But anyway, that type of latent variable model suggests that you can, if you can appeal to this underlying latent variable model, you can interpret betas in terms of it. If beta is 0.5, it means you increase your predictor by 1, you can change by about half a standard deviation in the underlying continuous scale. Half a standard deviation instead of just half, because the standard deviation is 1 for the standard normal, which is used for this link function. Well, let me just finish up by showing you a couple things you can do to go back to the probability scale. It might be a little easier to interpret. And I'm going to skip over the first of these and show you something that connects with what we talked about earlier. I wrote a paper a few years ago with my Italian friend Claudia Tarantola after a conference in the Netherlands, where we showed this idea of that was used for binary data and extended to ordinal data, of doing things like taking the average differences of probabilities or average rate of change in probabilities rather than dealing with odds ratios. So for instance, if you have a quantitative predictor for an ordinal model, and you look at one of these models for cumulative probabilities with main effects, you can have monotonicity if you look at the chance of the lowest category or the highest category. The ones in between, it goes up and then down or down and then up. But the extreme categories, which are usually the ones you're mostly interested in, are monotone. So for instance, you could look at the first category, and for the n observations, look at the average rate of change as that particular varies, an instantaneous rate of change for just to give an indication of how the effect of that predictor xk is on how fast the curve is going up or going down. And you can do that also for the highest category. I'll show you an example in just a minute here. If instead you have a binary predictor, instead look at the average difference of the chance of being in category 1, for instance, for the two for the two levels of the predictor and the chance of being in category C. Let me finish up with a quick example to try to make this a bit more concrete. Another data set shown to me some years ago by a professor at the University of Florida was interested in modeling a person's mental health. And they were looking at a measure of mental impairment. A person was interviewed by a clinical psychologist, asked all sorts of questions, and then characterized in terms of having really good mental health, or some mild impairment, or moderate impairment, or more severely impaired. So ordered categories, and this is the response variable, of the various predictors used, what seemed to be most relevant were the socioeconomic status, of a sort of a summary measure having to do with education and income. Here was just categorized as high and low for simplicity. And how many life events a person had experienced in recent years. A life event, something like a death in the family, a divorce, losing a job, moving. And there's several questions asked. They're accumulated into an overall index, which in the sample fell between 0 and 9 with a mean of about 4. Okay, so we're going to model mental impairment in terms of these, but try to use these simple probability summaries of the effect. So I read in the data set, there's the mass library, and R has a function that can fit these sorts of ordinal models. I first used a probit link to model impairment in terms of SES and life events. Probit Y, just so I could have some correspondence with the underlying normal regression model for a continuous response. So for instance, when I look at the life events, we could think of that as being saying that there's an impact of about a fifth of a standard deviation on impairment going up in mental impairment for every 1 unit change in life events. Anyway, a positive impact of life events is life events goes up, more likely to be impaired. Negative effect of SES, higher SES, less likely to be impaired. So let me finish up by just showing you how we can look at the extreme categories, well or impaired, for fit either with a probit or logit link, and then come up with these simple summaries that don't involve using odds ratios. I should have mentioned, by the way, some time ago, I apologize for this, that in this sort of traditional model, because you're dealing with a link that typically involves using the odds, the betas, again, refer to odds ratios, but this time using cumulative probabilities. They're even a bit more awkward than with binary data. So we're looking for an alternative to the odds ratio. Okay, so here we fit using the logistic link, which is probably most popular in practice. Again, negative effect of SES, positive life events on impairment. So we have a function we developed. We can look at the two extreme categories, well and impaired, and get summary effects that say, for instance, well, for SES, for the well category, high S, you estimate to be about the higher SES to have about a 0.198 higher chance of being well than lower SES. So that's just estimated difference of proportions, the chance of being well for the two groups, high and low for SES. Life events is quantitative, so that says for every unit change in life events, as life events goes up, the chance of being well goes down by about this much for every 1 unit change. Whereas if we're looking impaired, for every 1 unit change of life events, you're more likely to be more impaired. There's a positive impact, but the chance of being impaired is 0.17 lower for high SES than low SES. Anyway, I know this is kind of probably a lot for some of you students to absorb who may not have seen anything of logistic regression before, but the point is, even though the models themselves can seem a bit complicated, we can always try to rely on these simpler measures that we can then later explain to people to give an idea of what these effects mean in practical terms. Okay, so some simple ideas. My own opinion is that this is something we always have to focus on as statisticians, biostatisticians, data scientists, where most of us end up doing some consulting with people in other areas who are not very familiar with the models, the methods we're using. It's always important to look for simpler ways to explain the results so they can have an intuitive feeling of just what the effects mean. And as I mentioned, the ideas extend to other sorts of models like generalized additive models and other types of more complex models for categorical data. So just mention, I finish up, I'll put in an ad for some books I've written over my retirement years where I've had to focus on things like this by having just a simple chapter on categorical data analysis or generalized linear models. For instance, for some years, I taught a course at Harvard in the fall to their PhD students. I ended up writing a book summarizing ideas of linear and generalized linear models. First book I ever wrote was a basic course for social science students, which I've occasionally been revising, and again, trying to show complex ideas more simply. Some years ago, I wrote a book designed for the most elementary course, what we call Statistics 101, that a lot of students have to take, where we, again, not assuming calculus or any mathematics, going to basic ideas of statistics. And I'll mention there's a very nice website. If any of you out there end up teaching basic statistics, there's a very nice website one of my co-authors produced showing apps for illustrating lots of basic ideas like sampling distributions and confidence intervals and significance tests. And the most latest book on, or the math stat type book, again, using R and Python to use simulations to illustrate some of these ideas. Okay, so most of my career I ended up working in categorical data analysis and writing books on that. But in my retirement, I've tried to do some alternative sorts of things, just out of fun and be doing some different things and still keep active. So thanks again to all of you for coming. And I'll stop there and be happy to try to answer any questions you have.
Okay. Thank you very much, Dr. Agresti, for your lecture. And now we are open for any questions that the audience may have. Okay, there's one question there. Is geometric mean likelihood a model selection measure? Is there an advantage in using it instead of the AIC and BIC criteria?
Yeah,
Can you read the question?
My seminar. This was something I came up with a student in Florida some years ago. We just took a geometric mean of all the contributions to the likelihood to have something on a 0 to 1 scale. We could compare non-nested models in terms of which tends to give a better fit. And as this question suggests, there's things like AIC and BIC for doing that, which I use all the time for model fitting. The one advantage of this alternative measure is it's on a scale of 0 to 1. So it's a bit simpler to interpret the numerical value. And the closer to 1 it is, the better fit you're getting. The closer to 0, the poorer fit. So it's just, the numerical range is a bit simpler to interpret. But yeah, I don't want to say it's better to use an AIC or BIC. It's just an alternative measure that can be used to compare two models. And of course, AIC and BIC have their own excellent justifications. AIC for trying to tell you how complex the model you need to get the best estimate of what the underlying complex reality is, and BIC sort of helping you figure out what the best model is from a Bayesian perspective to analyze the data. So not really an advantage or disadvantage, just an alternative thing you can do. And I didn't really have time to talk about that and rushing through things today, but I want to put in a plug for that just because it's an idea one of my students and I had many years ago, but haven't really, I don't think it's been used too much since that paper was published. Okay, another question?
Can you read what are your recommendations for dealing with missing data?
Oh boy, wow, that's a tough thing. Wow, good questions here. Yeah, I don't have any magic solution. There's some good books that probably you know about various things you can do. For instance, a book by Little and Rubin. It's the book I focused on when I was trying to learn about this, to try to use methods to try to approximate what you would get if you did have missing data. I don't have anything new to say there for categorical data. There isn't also out there for regular quantitative data. You just learn about things like missing at random, missing completely at random, what those things mean, and think about how much you can assume based on your particular application, and then try to use some sort of a method to adjust for the missingness, realizing there's no magic cures. So nothing new here for categorical data, I don't think. And I have to admit, this is something I always wish I knew more about, because in a lot of the applications where I was dealing with helping friends, they had a fair amount of missing data. And it is nice that there is now more software that allows you to use some of the mechanisms for adjusting for missing data.
Okay. Is it reasonable to use squared predictors to evaluate the odds ratio?
I don't think so. If you want to explain why you would do this, I'm happy to hear. But the odds ratio just with regular predictors can be awkward enough to interpret. The one thing I mentioned about squaring the ratio proportions to give something more, mentioned how the odds ratio relates to more of the square of ratios. That was just an interesting side point that someone pointed out, but not something you want to do in practice, I don't think. One thing I'm trying to emphasize today is you don't have to just focus on the odds ratio. Think about how these other measures that can be easier for people to understand, like a ratio of proportions or a difference of proportions, and at least try to come up with some estimate for those, even if you use logistic regression, which is based on the odds ratio. So thank you for the question.
Next. Does the average marginal effect allow interpreting how much the probability will change on average for variations in an explanatory variable X?
Well, the version of that for quantitative variable does that in the sense that it gives you kind of an average slope. When you look at all the n observations and each place get a tangent line to the curve and average all those tangents, you're looking at, in a sense, variation in the range of the explanatory variable. I should mention there's other versions of these marginal effects, for instance, looking at just a typical value, like maybe the middle of the range, and getting estimated differences there instead of just averaging over all n values. So interestingly, I don't see statisticians using this much. I think it is better known among social scientists. I've seen this mentioned more in books that are devoted towards teaching statistics to social science students. So anyway, my quick answer to this is yes, for a quantitative predictor, that's basically what you're doing by looking at all the possible values of X and averaging all those rates of change.
Okay. Alice, he showed, he showed that. Okay, the question is, he showed you, of course, that he always used a large number of data. How could this be done in a situation with a limited number of experimental units?
Yeah.
Yeah.
All these methods I talked about today could be used regardless of what n is. See, what I didn't talk about much is for each of them, you can get a standard error. So if you just have a few observations, you're going to have a big standard error. And okay, you come up with a summary measure like an average difference of proportions, but then you may have a big standard error to force you to realize you don't have a good estimate of what it would be for the entire population. So yeah, that's a good point. You need to take that into account if you've got a limited number of experimental units. It can be a little more challenging to know whether your model fits well or not, but to the extent that you can use the model, you can still use these summaries just fine.
Okay. Is there any other question? No more
I
questions?
appreciate you all coming so late in the day. I know it's late there, 6 o'clock for all of you. Hey, 7 for me, so I'm about to go have some dinner, I think. I hope you'll be able to stay awake. If not, maybe I gave you all a chance to sleep a little bit the last hour. But anyway, I appreciate the invitation. And I hope I do get a chance to visit Brazil again sometime in my life. I know, like all countries these days, there are problems. I've had some problems with the environment recently in the South, and we have political issues on all these countries these days. So various problems, but it's a wonderful country, and I really feel very lucky that I had a chance to visit a few times. So thanks again.
Before we leave, I still have one question, a last question maybe.
Yeah.
What you can say about, nowadays we are using a lot the machine learning techniques for prediction. So what's your thought about using like a logistic regression, and people compare these with other machine learning methods or statistical learning approaches? Of course, there's a problem with like interpretability or prediction, right? So what's your thought about this?
I think you hit it on the head there, Luis. Yeah, if you got a huge amount of data, something like a neural network may end up giving you better predictions than logistic regression. But the issue is, if you are in an application where it's important to determine the effects, which variables have an effect, how strong are the effects, logistic regression is better for that. So yes, some of these machine learning methods can be very good for predictive purposes. If that's your main purpose, then you may want to put more emphasis on that than logistic regression. But in my experience, most applications I dealt with, I was dealing with scientists, social scientists, who really want to figure out what is significant, how important is the effect, is it practically significant, yes or no, of all these variables, which is important, which isn't. And for that, you need more traditional regression type models. Mm-hmm. So it's great to learn about these machine learning methods, and that's certainly the hot subject these days. And it's great if the students there are learning some of that. I wish I knew more about them myself. I've tried to learn a bit about them in recent years. It's a challenge to to be able to get to interpretability with them. So yeah, that's an interesting challenge there.
All right. If there's no more questions, maybe we can leave, and thank you once more for your excellent lecture. And I hope we can keep in touch somehow, like you are retired, but still working and very happy and strong in your research. And I think so maybe we can have in touch in the future.
Well, you're very kind comments. Okay. Thank you very much. Again, thanks to everyone.
All
Bye
right.
now.
Bye-bye.